All right, hi everyone. We're just waiting for a few more seconds for all the people to arrive. All right, I think we're ready to begin. I see there are some 43 of us on Zoom and more than 50 on YouTube. So numbers are going up. So I think a few more people are coming in. But given it's 8 o'clock, let's start. Let me begin by first welcoming you all to the first in a series of Astronomy at Home events. My name is Mario Juric. I'm a professor of astronomy at the University of Washington. And I'd like to really briefly welcome you to this series on behalf of UW's Institute for Data Intensive Research in Astronomy and Cosmology, also known as DiRAC, and on behalf of Astronomy on Tap. So let me also introduce my UW colleagues, and as I call you out, let's wave to everyone. So Nicole, who's one of the graduate students here, who is an Astronomy and Tap coordinator and will be helping manage this stream. Meredith, one of our researchers at UW. Nicolina, one of our admins at UW, and of course Jim, who will be speaking this evening. You'll be interacting with all of us as this event goes on. So the talk this evening is the first in a series that will feature UW astronomers talking about our work and what's new in astronomy. So through these, what we hope to do is to kind of share and give you a glimpse of what we do, what it's like to be an astronomer, to bring you some of the excitement and new discoveries and research really that's still ongoing, even in these really weird times that we live in right now. So these events are intended to be for everyone who's curious about space and astronomy. There is no deep prior knowledge required, just some kind of curiosity and enthusiasm. They're also meant to be interactive and conversational. So what we'll usually do is begin with perhaps a 20-minute talk, but then leave plenty of time for Q&A and chatting with the speaker and all of us present. So to join that conversation, you can either connect via Zoom. If you're watching this on YouTube right now, you can switch over to Zoom if you go to dirac.us/Zoom. Or you can just type your questions and comments into the live chat on YouTube, and we'll pick them up from there and relate them to the speaker and to all of us. If you are on Zoom, to ask a question right now, everybody's muted. So to ask your question, click on the raise hand button in the participants panel, and we'll unmute you once Jim is done speaking. There'll also be a live interview over on Instagram immediately after the Zoom event, so around 8:45 or so. One thing to be aware of, or to make you aware of, especially those of you who are on Zoom, is that we're both streaming this and recording it. So there'll be a recording of it on YouTube. So if you're worried about being recorded, now's the time to turn off your camera. If you're not, welcome, and please keep it on. So that's all for me. I'll now hand over the virtual mic to Nicole, one of our grad students at UW and the Astronomy and Tap coordinator, to say more about what Astronomy and Tap is and the Instagram live session, and to introduce Jim, our speaker for tonight. All right.
Thank you very much, Mario. Welcome to Astronomy at Home. This is so exciting. I've got my, diagram view so I can see a bunch of you who do have your cameras on. It's really awesome to be interacting with you all astronomy enthusiasts in this new venue. We definitely miss our peddler home, but it's really great to be able to bring astronomy to people who may not be in the local Seattle area. I'm pretty sure I saw on the YouTube chat that somebody's calling in from Japan, super far away. That's amazing. So welcome. And yeah, so for those of you who are maybe new to Astronomy on Tap in general, you know, we usually host these events at a local brewery. We have, you know, maybe a drink or two, and we enjoy some science from a local scientist. And I'll be introducing ours in just a moment. As Mario said, we're going to be doing this series moving forward, and every 2 weeks on Thursday night is the plan to be bringing astronomy to you right from the comfort of your own couch. So we hope that you can join us. Just to give a little shout out to Peddler Brewing Company, which is our usual hub where we host our Astronomy on Tap. They're actually doing, they're giving us some discount codes if you're in the Seattle area. So you can go to there. I'll put their link on the chat, but they have like the hashtag astronomy15 discount code if you wanna, you know, next time you can have your Peddler Brewing beer with you, and you can enjoy Astronomy on Tap and pretend that we're all together again. So without further ado, I want to introduce our speaker for the night. He is a former UW graduate student, so I aspire to be, you know, in a similar place as him someday. He is an associate director of the DiRAC Institute, who is the co-host of this event, and more recently, a brand new research assistant professor in the University of Washington Astronomy Department. And so I have the honor of introducing, for the very first time, Professor Jim Davenport. Take it away.
Okay. Can everybody hear me? Is the mic okay? We set up? I see thumbs up. Awesome. Thank you. Thank you. Thank you. And yeah, let me echo what my friends and my co-hosts have said. Thank you all. I'm super amazed at how many people are here on Zoom and on YouTube. And thank you for coming and supporting your local science and your local scientists in this unusual time. And make sure you're supporting your local businesses. We're trying to as well, to give shout outs to Peddler and other local breweries and other local businesses that are also struggling at this time. So thank you for joining us. We're going to talk about 20 minutes, 25 minutes, something like that. I hope this will spark some interesting conversations. Hopefully we can have lots of good Q&A. I'm going to swap over to my slides here, but hopefully you'll see my little thumbnail in the corner at the same time here. So let me make my screen share happen. Okay, and hopefully you are now seeing the title slide for this talk. Okay, so my plan tonight is to talk a little bit about what we are going to call the most mysterious stars in the galaxy. And this is, of course, a clickbaity kind of way of saying just some really cool things, because they're all really good stars. They're all very mysterious and very exciting. But these stars may be some of the most mysterious and most exciting to study. And it's something that I've been excited to work on as a part of DiRAC for the last couple of years. Maybe I'll click on the right window. There we go. So this project has been primarily led at the DiRAC Institute, as Mario said, the Data Intensive Research in Astronomy and Cosmology, or Astrophysics and Cosmology, here at UW. Here's a couple of just pictures from our social media of various meetings and people thinking very thoughtfully about things and presenting posters. This is a collaborative institute. We feature researchers at all different ranks within the academy. So we've got students, graduate students, research scientists, faculty, postdocs, programmers, people who are very focused on science, very focused on data. We try to bring in a wide range of people to come bring the best ideas and the best sorts of fusion of science, data, and programming and algorithms that we can. And there we go. All right, now my buttons work. Here we go. Okay, so we study a wide variety of things. Some of us are experts in stars, like myself, and exoplanets. So we study little dots going around parent stars, like transiting exoplanets at UW. A lot of us work on these kinds of things. And at the totally other end of the spectrum of mass, we work on things like supernova, explosions, cosmic explosions that will outshine their host galaxy. On the top right here, you can see an example of a supernova from a recent survey. This star exploded and outshone its parent galaxy for something like 10 or 20 days. And on the very bottom, we even study things like asteroids. Here's an example of a tumbling asteroid that we were able to observe with telescopes that UW has access to. So we are really specialized in doing what we would call variable star or variable time series astronomy. So we're looking at how things change in their brightness as a function of time. All three of these things are very different objects in the cosmos, and they all change their brightness, right? Some of them get fainter, some of them get brighter. And they're at all kinds of different distances from the Earth. Now, one particular survey that I've worked on a lot, the story that we're going to tell starts with, is the Kepler survey. Now, this is a space telescope that NASA launched. It has now since finished its mission. It's no longer operational, but it was in outer space, and it studied one large field of view, about 116 square degrees, shown here in a picture from the ground. A large field of view, and it just stared at this one area of sky for 4 years with sort of an unblinking eye. And the goal of the Kepler mission was just to try to see these little dips, these we would say little transits. So this is like the exoplanet here that I pointed out that goes around its parent star, where you see the light goes down just a tiny amount over the couple hours when the planet is moving in front of its parent star. Kepler's job was to try to find these. And to find something like this, you have to stare at one patch of sky for many years. If you wanted to study the Earth, you would want to study it for at least 2 or 3 years, study this star, waiting for the Earth to go around once a year, where we'd have a chance alignment and could block the sun. So in total, they studied something like 200,000 stars with the Kepler mission. And this becomes an amazing wealth of data. You've got 4 years of data on 200,000 stars. It's really unmatched in terms of like the detail that you can see how stars change very slowly and very quickly over time. Okay, so after a few years of operation, Kepler launched in 2009. It operated for a few years, and in 2015, a fascinating paper came out that surprised a lot of people in the community. And this was called Where is the Flux, or WTF. Now, KIC 846852, that's the sort of catalog phone number that we know this star by. And in 2015, this really fascinating object that we now have called Boyajian star, or you'll sometimes see it called Tabby star, named after the first author, Professor Tabitha Boyajian. This object was discovered. And what I love about this, you see the top part of the title of this paper. This is the actual screenshot of the paper. The paper is called Planet Hunters, paper number 10, paper X. And Planet Hunters is a citizen science data project. So real people, not astronomers, are going through and looking at all of the time series data from the Kepler mission, and now the K2 and the TESS mission and other missions. And they're making real discoveries. And so a lot of the authors here on this paper, not all of them, but a lot of the authors in this paper are just what we would call citizen scientists, just regular people who are excited about science and are contributing to science. So at the end of the talk, I have a link to this, and I would encourage you to all go check this Planet Hunters project out. So the Planet Hunters crew discovered this very fascinating object, and it was so strange that they titled their paper WTF, which I absolutely love. And I think somebody's got their microphone off. If you could just go ahead and hit mute, that would be really awesome for me. Okay, so this object is very mysterious, as I alluded to. The Atlantic is the outlet that I first saw coin it the most mysterious star in our galaxy. So this is where I borrowed this talk from. It indeed is an extremely mysterious star. This paper got a lot of press, both within astronomy and in the public media, which is great. You can tell it's a legit cool object because it has both its own Wikipedia page and its own Twitter account, which I love. And so you can go follow Boyajian star on Twitter. It's not guaranteed that it will affect the astrophysics that the star does, but it's a fun thing to do. And you can go check it out on Wikipedia. Okay, so here's Boyajian star. Oh, and of course, if you're going to get a lot of popular media, you're of course going to get some of this media. Has Kepler discovered an alien megastructure? Is it aliens? Is it UFOs? Is it aliens? This is, of course, whenever we paint scientists as not having an answer to a question, we immediately have to come to this kind of press. And what I love about this is twofold. One, Ian O'Neill is a really great journalist and writer. We follow each other on Twitter, and so I want to make sure I just give him some love and not tease him too harshly about this, because he's a fantastic science writer. And second, I love this picture that they used. And Ian told me once they were on such a tight deadline that he wasn't actually sure what the picture really was. And so I love this because if you look at the little alien spaceship they used, it looks exactly like the ship from Firefly. And I have no idea why. Spoiler, we did not discover aliens or Firefly in the Kepler data. But I always think this is a hilarious thing that they included in the public media. Okay, so what is it? Here is, to the scientists out here, here is the amazing discovery that has baffled us now for 6 years. This is a series of very unusually shaped dips in the brightness of the star, lasting in some cases a couple days or in some cases many days. This may not be that exciting, but let me lay some groundwork for you, and I think you'll appreciate how strange these little modulations in the brightness over time are. So there's a few of these dips. They're spaced out over years. We have them in sort of on the x-axis in time. So in funny, this is days since launch of Kepler. So on around day 793 of the mission, the star got about 15% fainter all of a sudden. And then something like 800 days later, there was a series of very strange changes in the brightness. Again, almost 10 to 20% in the brightness. Really dramatic variation from this star. Oh, and here's a zoom in on this second series of events. And you can see it's incredibly detailed, lots of little wiggles, lots of little structure. And these aren't artifacts in our data. The Kepler Space Telescope was in space. And so there's no atmosphere to blur the image of the telescope. There's no sun to rise. You don't have any of the problems that you have on the ground when you're trying to observe stars. Nothing's twinkling up there. So every little wiggle you see in this data is real. The star had all these small little modulations and then big variations in its brightness. You can imagine this big star just changing its brightness by 10 or 20%. If the sun was 20% fainter on a clear summer day, you would definitely notice. And to, I think, hammer this point home a little bit, if we expected these variations of brightness to come from, say, a circular object like a planet moving in front of its parent star, well, you would expect this nice little sort of bowl-shaped feature that we see on the left. This is what we call a transit-like curve, when the planet transits or crosses in front of its parent star. This is the kind of thing that Kepler was built for. This is its bread and butter. You see this nice symmetry, maybe a flat or slightly curved bottom as it goes over the surface of the star, or the planet does, and then it comes out nice, symmetric, in and out it goes. And if you think, okay, a circle passing in front of another circle creates this nice sort of U-shaped, and then you look on the right and you see this series of just wild modulations, you might think WTF. You might think, where did this flux go? This is absurd. What shape of thing could possibly have caused, and how big must it have been? A planet like the Earth might cause a 1 part in 1,000 change in the brightness, and here we're seeing changes that are 20%. These are really dramatic variations for this star. Something very strange has either happened to this star or is moving in front of this star. And of course, this is why the media got all hyped up that maybe it's aliens. So what is Boyajian's star? Well, at first glance, when the mission started, we thought it was a totally normal F-type star. It was not known to be special at all. It's not part of a binary. It doesn't move in a particular strange way. It doesn't have anything unusual about it. It was a normal F-type star. Now, F-type, that's just astronomer speak for the temperature class that it's in. The sun is a G-type star. It's a little bit cooler than this. This is a normal, boring star. I mean, okay, they're all cool. They're all interesting, but this is a boring star. This star just sits there and has a normal life, and we don't expect anything surprising from it, right? Until all of a sudden something very weird and surprising happens. So what? WTF? What is this? Something very strange has happened to Boyajian's star, or again, is happening around it. There's a lot of theories. There's a whole litany of papers that have come out in the last 5 or 6 years postulating it could be this, it could be that. Some of my favorite theories right now, the theory, in fact, that Tabitha Boyajian and her team posited in their discovery paper, was that this might be a series of very strange comets. So you could imagine some family of comets floating in front of the star. They'd have to be really whopping big comets, real big comets, to move right in front of the star. And sort of the weird, asymmetric, slow changes in brightness might be because they have big tails and material. I mean, it's possible. We could imagine creating a bunch of comets and putting them in magical orbits around the star, and it seems possible. Sort of a similar theory about this might be that instead of comets going around the star, that maybe you had something like 2 planets smashing into each other, creating a huge chaotic debris field. And now that seems like a very unlikely scenario perhaps at first, but remember the Earth and the Moon formed in a similar kind of scenario. When the Earth was very young, billions of years ago, a planet the size of Mars this is our best guess, ran into the Earth, smashed into the Earth. And what formed out of the cloud and garbage that came out, sort of this debris cloud that you can see in the artist rendition here, what formed out of that was the moon. And this is why the moon and the Earth have very similar, almost identical compositions, is that they formed out of this collision. Now this are only hit by one sized object, and hopefully it won't be hit by any more anytime soon. We don't need any more moons in this planet. This is an unlikely scenario for any given day on a star, but we know that it can happen. We know that things can accrete, we would say, run into each other, like the way a snowball grows when you roll it down the hill. We know that dirt and dust and gas get clumped up together in the early formation of a star. And so maybe Boyajian star has an active planetary disk around it that's just full of debris. This seems plausible. I will say both of these scenarios and lots of other scenarios would usually have other indicators that something else is going on. There'd be signs of dust, or we would usually see lots of light coming out in the infrared. Infrared, of course, is the wavelength of light that you glow at because you're a warm body. And so too, this warm dust would glow in the infrared. And so we don't see a bunch of extra light in the infrared. So you have this weird clumpy stuff possibly moving in front of the star. Now, there's a whole host of other possible explanations, like wild things. It says my internet is unstable. Hopefully this is still understandable. That there may be wild things that the star itself is doing. We don't know. We have effectively no theories of what would cause the star itself to be dimming so wildly and so rapidly. So our best guess right now is something dusty and clumpy orbiting around the star. One of my favorite diagrams about this, which I think is a great take-home message from this whole talk. One of my favorite diagrams of this came from a paper, I guess 3 years ago now, which they posited that the modulations we saw were due to some kind of asteroid cloud. So we would call these Trojan asteroids, asteroids that are companions moving around gravitationally linked to some giant unseen planet. So in this case, the star is the nice little yellow circle. There's an unseen planet. The planet wasn't quite in the right geometry to eclipse or pass in front of its parent star. So we don't see the planet. Or if we do, we only see perhaps the rings. So that would be this major smooth dip that we saw here on 2011, March 4th, here in the middle. So this cartoon is aligned to that dip. So maybe only the rings would graze the star, and we would see some very smooth dip. And then sometime later, these asteroids that are caught in the gravitational resonance or the orbit with the big planet would come by, and they would pass in front of the star, and then we would see these chaotic dips. And that it was just unfortunate that so May 1st, 2009 here, this is the beginning of the mission. And so these dips, there might have been more, but we just didn't have enough data. Kepler was still launching and heading out to its orbit. So we don't have any data before this. Now, this is a really cool hypothesis. We don't know if it's true yet. There was a prediction that there would be a secondary eclipse in 2017, and that was not seen. So that didn't strongly rule the scenario out. We didn't know if it would have a secondary eclipse, or that would be a point when the planet goes behind the star and makes a tiny dip, a smaller dip in the brightness. But we didn't see that. So not necessarily a deal breaker here. But what I love about this is that it makes a prediction, a good prediction, that in the early months, somewhere around early months of 2021, these major dips from the trailing set of asteroids should come back around, and we should see this whole series of events happen again. Now, again, this might seem like kind of a wild theory, but this is exactly the geometry we see for Jupiter in our own solar system, that there's a large family of so-called Trojan asteroids that move around in the orbiter with the sun at the same orbital radius as Jupiter, but separated by this a big planet, or maybe super Jupiter planet, could trap a lot of asteroids with it in the sort of gravitational dance and drag them around. So it's totally possible. We'll know more next year. And so this kind of prediction that in the next few years, even though the Kepler Space Telescope is no longer functioning, has rallied a lot of people on Earth to point their telescopes at Boyajian star as regularly as they can. So ongoing monitoring has been going. There have been some very small dips, but nothing like we've seen from the Kepler data. So hopefully this system will still have a lot more activity left in it for the next few years. Okay, so this is all background. Boyajian star object is fascinating, but it is one object, only one object, and we loathe a sample size of one. That's not helpful for making predictions about the universe, where we came from, where we're going. So we have a very big fundamental question. Are there other Boyajian stars in our galaxy? If these are, for example, asteroids or a planetary collision or a planet smash situation, knowing the rate that we might see these things tells us about how often these giant asteroids and these giant planets hang around in other star systems like our own Earth and Sun system. We weren't there when the Earth and Sun formed. It would be nice to know what those kind of systems looked like when they were younger or when they're older even. So knowing statistics, the rate that we see these kinds of things is really important for understanding our place in our galaxy. And so this is the survey, this is the project that we started here at the DiRAC Institute just over a year ago now. So DiRAC and the University of Washington are members of the ZTF Survey. That's the Zwicky Transient Facility. Now, this is a picture of the telescope here on Palomar. The telescope is operated and the survey is operated by Caltech, so there are partners in this survey here. It's a fantastic data set. Basically, this telescope has a giant camera and it surveys the entire northern night sky every 3 nights. So it spends all, it's semi-robotic, mosaic pictures of the sky over and over. It's surveying something like 30,000 square degrees over the course of the year. And it's been doing that now for about 2 years. And it's surveyed over 1 billion stars. It's approaching 2 billion stars. Now compare that again to the numbers we had from Kepler. So 30,000 square degrees versus 100 square degrees. Over 1 billion, now almost 2 billion stars versus 200,000 stars. And so even though the data is not as precise, we're not in outer space, we don't get continuous unblinking eye that outer space provides us, the numbers game really helps. We've sampled an enormous fraction of the sky and a huge chunk of our galaxy with this survey. And so this is like the perfect test bed to ask this question. Do we see other Boyajian star-like objects? Okay, here's just some glamour shots. On the left is an example of the coordinates on the sky that the ZTF survey has mapped. You can see it's most of the northern sky here in astronomy, latitude and longitude coordinates. And on the right, this is the commissioning image, and it's a picture of Orion. It's very beautiful. ZTF is a really awesome survey. So thumbs up. Thank you, Caltech, for being great partners in this. Okay, so the canonical object here, Boyajian star, the WTF star, was discovered at planethunters.org by real citizen scientists, real astronomy enthusiasts who used their eyeballs. The sophisticated algorithm to find this thing was their eyes. And I return to this point of being like a fascinating and inspiring and yet frustrating point of this whole story, that we had this amazing object. Some of this data was on the ground in our databases, in our computers for years, and no professional astronomers took notice of it. Nobody said, this is a weird object. Instead, it took eyeballs. It took humans to notice, this looks very strange. What's up with this? Now, when you have 200,000 objects, the power of the internet works. We can rally hundreds of people. You saw the author list for this paper. There was dozens of people who participated in finding this object and characterizing it. When we have almost 2 billion objects, that requires a lot of eyeballs. And right now, we don't have access to that many people who would be interested in doing this. But again, go to planethunters.org if you're excited about helping find really cool stuff in all areas of science, not just astronomy. It's linked up to the Zooniverse family of projects. If you're interested in contributing to these kinds of projects, human eyeballs are really important. So the solution, of course, as the name of DiRAC implies, data intensive. We're doing intensive data analysis of over 1 billion objects with our software. So on the right is just the random screenshot of some code. We have to write code. We need the computers to do this for us. We can't go through the 1 billion objects ourselves. What I also love about this project is that it's really at the essence of what DiRAC is about, and really what the astronomy department at the University of Washington has always been about. It's bringing together expertise across the entire domain of astronomy. So in these photos here, you have people who work on supernova, people who work on giant stars. I work on the tiniest stars. Some people work on the most massive stars that explode. You've got people with software backgrounds, people who are working for different surveys and different projects and different missions. There's a huge number of people who have contributed to this, just the main people here on the left, but we've had such productive conversations and presentations with people all over the Institute and the university. So it really is a collaborative effort. And to go back to something that Mario and Nicole both said at the beginning, in this time when we can't be together, when I have to be in my basement and talk to you live via the internet, having this collaborative environment, people who work well together, already established, has made this project really satisfying. And so on a personal note, this is the best meeting that I have every week. Every Thursday in the afternoon, it looks like somebody's annotating the slides there. Every Thursday in the afternoon, we meet and we chat and we talk and we try to dream up better ways of finding these interesting objects. And so this is a really wonderful kind of project that if you're working in a group setting like this, I would encourage you to take these projects and use this time to try to make collaborative science a go. Oh, and I love this photo on the right because here, Colin, one of our arguably one of our most talented programmers and a database expert. Here he's measuring, we're trying to guesstimate the duration of an event. And he went into his office and he found a ruler and he's measuring the duration on the screen with a ruler, trying to understand this event. So we really do use the most sophisticated technology that's available to us. Okay, so we started this project about a year ago as a collaborative thing that we would spend an hour a week together writing. Now, I could go on for a very long time about how we fought with weird bugs in our data, in our software, strange, unexpected attributes of the ZTF survey that we hadn't experienced before. This part, of course, is the hardest part and the most boring part. And so let's start to move towards the end of this and let's look at the good stuff. We have a lot of neat, what we call dipper events. So we characterize Boyajian star as being a normal star that has a sort of constant level of brightness most of the time. And then once or twice in its total observation span of several years, and so ZTF's only been going for about 2 years, so about approximately one really strange, unexpected, unexplained dipping or dimming event. And so here are 4 examples that I just pulled this afternoon from our code that look like very interesting events that I would very much like to follow up here. I've emphasized them with the sort of PowerPoint blue lines so you can kind of follow the eye a little bit. And on the right is a very uninteresting, well, it's very interesting, but it's uninteresting for this survey, bit of junk, but we find a ton of these too. We think that the Boyajian star dips are very unusual, not only because they're rare, but because they're very asymmetric or have lots of wiggles or structure. The one on the right, we would say, this is pretty symmetric. We think this is just a scaled up version of that planet moving in front of its parent star. This might be 2 stars, one moving in front of each other. Now, these are really interesting, and part of my work focuses on these what we call binary star systems, but we try to throw them out. And this is actually one of the sticking points right now is trying to really tell the difference between the interesting sort of asymmetric, sort of sawtooth shaped dips on the left and the sort of symmetrical eclipse shaped dips on the right. This is an interesting area we're working on right now. So there's lots of interesting candidates, something like 60,000 candidates that we were playing with today. Again, probably too many to really vet all of them by eye. So we're still trying to lean on the computer and the machine learning software that we can develop to tell the difference between what's good and what's junk. And yeah, just to again highlight, we like events like this, things that are sort of smooth at times or asymmetric or have lots of weird shapes. This one to me was just a good example that it sort of mirrors what we expect to see from the actual Boyajian star. And one other sort of bit of interesting trivia is that Boyajian star, it's a little bit hotter than the sun, a little bit brighter than the sun, but it's a normal star in the sort of the middle of the pack here in terms of its brightness and its temperature. This is the sort of astronomers' basic diagram. We would call this a color magnitude diagram or a Hertzsprung-Russell diagram. The point is it maps the brightness versus the color. So there's tiny, cool, faint dwarfs on the bottom right, massive giant stars on the top. We really do call them giants and dwarfs. That's the term we use. Boyajian star itself, I've put on this diagram in a little blue star. And you can see that this dipping behavior is coming from stars all around, in both hotter and cooler, more massive, brighter and fainter. So lots of stars are exhibiting this kind of dipping behavior. So there's a lot to study here. That tells us it's not just something special, we hope, to these sort of F-type stars, but maybe this kind of dipping behavior is endemic to all stars occasionally, rarely. All right. And in conclusion, of course, in astronomy, so many mysteries await our discovery. The Kepler mission, which of course now is no longer operating, but its successor, the TESS mission, which launched a couple of years ago and is now in its second year of operation, these telescopes are mapping the sky, looking for more transiting exoplanets, and along the way are just churning out amazing discoveries for stars, for supernova, for everything else that goes bump in the night. And then I'm extremely excited about the Vera C. Rubin Observatory, which was formerly called the LSST Observatory, pictured here on the right. This 8-meter telescope is going to survey the night sky, just like the ZTF survey. About every 3 nights, you're going to create this incredible map of the sky, and you're going to be just pumping out amazing discoveries from this data set. And so I will absolutely conclude by saying, I hope we see you next time when Professor Željko Vezic will talk about the greatest movie of all time, which is the Vera C. Rubin Observatory's LSST program. And I hope you keep looking up. I hope you're well, and I will thank you.
All right. Thank you so much, Jim. And we're going to unmute just a few people because we're astronomers and we love applause. So thank you so much. And you can use your little chat reactions also to applaud as well. We have some time for some questions. And so if you want to use your reactions or maybe even type a question into the chat, I can unmute you and you can ask a question to the speaker. I'm in gallery view and I am looking for hands. Aaron Howard, I see you. I'm looking for.
Hi, Aaron.
All right, Aaron, you are unmuted if you want to ask your question.
Okay, I think I finally unmuted. So great talk. I'm absolutely fascinated by the idea of Trojan asteroids being the cause. And I'm curious, has anyone created a model of, say, how Jupiter and its Trojans would look if we were as far away as the Tabitha Star?
Yeah, I think that's actually what this paper based their model on. The issue is you need to scale these up to really big asteroids, right? The thing that's so perplexing and frustrating is you would need asteroids that are like planet-sized asteroids. They'd have to be really big, or you'd have to have such an incredible number density of asteroids to cause a 20% flux variation, 10 to 20%. So the asteroids we see on Jupiter, if we scale them up, would be imperceptible. Even if you saw the swarm of the Trojans, it would probably be imperceptible. So it's a good model for the sort of geometry of what we expect, but it really has a hard time explaining how you get such big variations. Yeah, it's really a good mystery.
Any other questions from the audience?
I have a couple questions from YouTube, if I can jump in real quick.
Absolutely.
So there's several questions on the chat. I'm going to condense 2 of them into one. One of them was asking if we are aware of any star systems in an earlier planetary formation stage where like planets haven't finished forming yet, and if there's anything that we could compare to there to see if it's similar to what we're seeing, and kind of along the same lines, if we could potentially use colors to learn about the materials that are present in the system.
Yeah, those are both really great questions. In terms of looking at earlier versions of our sun, of our planetary, I would say the ALMA mission right now has been, the ALMA telescopes has been a great example of being able to take pictures of early solar systems that are forming. And I think just a week or 2 ago, we saw a picture of a baby solar system with a planet actually forming. You can see the dust and the gas around it. Really, really amazing. It's a giant planet forming around its parent star. But again, not good geometry or not ability to see the Trojan asteroids that we would need to get these kinds of dips. So it's not exactly a good analog. We do see a lot of young stars in Kepler. And one thing that young stars do is vary a ton. And so we call these YSOs, young stellar objects, and they are absurdly variable. So the problem is actually they're not quiet enough. Most YSOs vary all the time because there's material swirling around them, sometimes falling onto the parent star. They're incredibly variable. And that's kind of our expectation for a young sort of baby star system where the planets are just beginning to form. They're not actually quiet enough to form something like Boyajian star. In terms of colors, yeah, so photometric colors, we would say, so this is like having a red piece of glass and a blue piece of glass, and you take a picture in both colors, and the ratio of the brightnesses of the dips, or the depths of the dips, I guess, in those two colors gives us some hint about the temperature and the temperature variations going on. So this actually is exactly what they're working on right now. Tabitha Boyajian and her team have like an ongoing monitoring program from the ground where they're trying to do multi-band, multicolor imaging of the star every few nights. And they have seen some dips, and there's a little bit of color information, but it's really ambiguous. And we haven't seen any of these. We've seen at most 1% or 2% variation. So we haven't seen these big 10 or 20% variations. So we don't know yet what those are. But that's definitely got to be part of the solution. The multicolor imaging is absolutely clutch.
Thank you, Jim. We have another question from Shocks here on the Zoom. Can you touch on why a dip was predicted, even though it didn't happen when the planet was on the backside of the star? If the planet wasn't passing in front of the star, why would it dip?
Right. So, okay, so the very smooth dip that we saw, I guess, in 2011, that's sort of this whole model revolves around the idea that dip has to be due to a planet with a giant ring, like a super Saturn kind of thing. And so the very slow dip that we saw is the rings and maybe a little bit of the planet moving in front of the parent star, the Boyajian's parent star. And so it did partially eclipse or partially cover its parent star, but the rings caused that nice slow dip in and out of brightness. And so the whole model is built on the idea that dip was due to this big ringed super Saturn. And then we know that Trojan asteroids should be at 60. The hand clock should be separated by 60 degrees in the orbital position. That's like the position they need to be at to be Trojan asteroids and to be stable. And so if we assume that the series of dips that was seen a couple years later is 60 degrees apart, then that is how you make a prediction. Because we don't actually know what the orbital period of this planet is. We don't know if it's like Jupiter, 5 years or 10 years or 12 years or 100 years, if it is a planet. We just have to assume that those asteroid cloud and the planet were 60 degrees separated. And if that's true, then the planet might have gone behind and grazed the star on the backside. But that was an uncertain kind of prediction. So we didn't see that, at least not from the ground. But again, the cloud moving back around in 2021 is going to be really exciting. So hopefully in about a year, I'll come back at Astronomy on Tap in person and give the update on, was there a cloud? Because we'll know in about a year.
I'll jump back in with a question from YouTube. This one asks, if I can find it, if somebody 1,000 light years from the solar system were to look at Boyajian star, how would they see the dips how would they see dips of us? Would they see something similar to what we're seeing of them?
Oh, interesting. Okay. So if I understand the question, so sort of twofold question. So how would they see on the geometry of Boyajian star system? And which way they were headed in space. And so you only see eclipses of planets, and you would only see these Trojan asteroids moving in front of the star if you're in the exact right alignment, right? There's no up in space. Everybody's not oriented upwards. And so you have to have just the right magical alignment so that when the planet moves in front of its star, you are right along that line of sight. So if they were 1,000 light years away from us, but in that correct line of sight, in that correct plane of orientation, then they would probably see about the same thing. Boyajian star is like 1,000. I should know this number off the top of my head, but I don't. It's like 1,000 light years away or something. So another 1,000 light years would make it about 4 times fainter. But you'd still see the sort of the same amplitude of modulations. Now, if you were 1,000 light years away and looking at us, and you were in the exact right orientation that you saw the Earth eclipse, we call that the Earth transit zone. There are a bunch of stars. There are hundreds or thousands of stars in that zone, that disk around us. And we think that that's a great place to look for, say, if you do want to look for aliens, that's a good place to look for them, because those are the people who would know that there's a planet around our star. So they should be able to see the Earth if they had a Kepler space telescope of their own.
Great. And then we have a few more questions in the Zoom. Let's see. Matthew Karasu asks, with high resolution, we could see what the individual shapes of the objects passing in front of the star. How close are we to improving our resolution?
Yeah, to actually, so this is a great point, that with enough, we would say, spatial resolution, you could actually see the shapes of things. So you would need a telescope like the size of the Earth's orbit around the sun to see the structure of an asteroid as we see them. You may be a little smaller, maybe something between around Venus's orbit, but you would need something that is like millions of miles across. That's how big of a telescope you would need to see the kind of shape of an asteroid in another star system. So it would be absurdly huge. Now, we've speculated about how to build such kinds of constellations of telescopes that might orbit around the be obviously expensive. I'm not saying let's not build it. I'm just saying it's maybe not our #1 priority right now.
Thank you, Jim. I'll jump in with one more question from YouTube. This maybe actually was directed at me, but I'm going to throw it at you. What is your favorite alternative theory to the asteroid field theory?
I mean, I do quite like the planet smash theory, just because we've not seen another example of the Earth-Moon system forming. And there's so much excitement about the formation of planets and modeling that, that if we had some evidence that a planet was forming a giant companion moon like our own, that to me, that would be really exciting. That really personalizes the system. So I like that. And of course, I have to say I liked in past tense, I liked the SETI angle, the aliens angle, because it just got people really worked up and excited. Both because it got people excited about disproving it, but also it stoked some legitimate interest in saying, well, at the moment we cannot disprove it, and we now can fairly well rule it out and say we think it's dust. We just don't know what dust and where it is. But I liked that because it did force very serious astronomers to actually say, but what if it was aliens? And you have to love when people have those sorts of walls broken down.
All right, I'm gonna wrap us up with one last question, looking at the time. Just as a reminder, before everybody checks out, we are going to be doing an Instagram live Q&A with Jim right after this. So as soon as we all sign out, I'll put the link in the chat, and so you'll be able to join us and have some more interaction and face-to-face with our fabulous speaker. But so to close us out, Biswara Banerjee asks, how exactly are you using machine learning to identify these stars? Like, I was interested to know a bit more about how you all are using machine learning in the images taken by the telescopes.
Right. So in this case, the images themselves, we're not doing any learning on. We're not doing any vision kind of stuff on them right now. We do, however, actually co-opt a bunch of computer vision algorithms to find things, which is cool. The telescope itself has a really complicated pipeline for taking the images and what we'd say reducing them down. Really subtle calibrations that it has to do. There's a little bit of machine learning magic in the scheduling, I think, about where to point the telescope. But in terms of what the telescope's doing, there's not a lot of what we would call classically machine learning. A lot of what we're doing and a lot of what we propose to do is actually to classify what we find. So we can find outliers in the light curves just using sort of basic statistics, how often we see an outlier data point. Most of our data has error bars or uncertainties on it, so we can make good predictions on whether or not a point is significantly a dip. What we don't have good statistics on is what the shapes of the dips or the various shapes of the dips are. And so that's something that we would like to use sort of clustering on. So some of our collaborators like Daniela Hook-McCothan and Kyle Boone are real whizzes with machine learning and with clustering and classification problems. So that's something they're working on right now. But it's something that you have to measure a lot of features on these dips. And some of them, one of the big problems, of course, is this data is really noisy, really gappy. The sun comes up, it gets cloudy, you'll have a fire or a big weather event, you won't get data for 3 days. And so you'll have a big gap in your data. So trying to apply a lot of canned machine learning or algorithms or any kind of canned algorithms really struggles when you have real noisy data. So it really is an interesting struggle.
Awesome. Thank you so much, Jim. And for those of you unmuted, let's give him one more round of applause. Thank you so much. And once again, right after this, we're going live on Instagram. Follow us at AOT Seattle, all one word. On Instagram, you'll find us there. And join us again next week, in 2 weeks on Thursday when Joko, our fabulous, I think one of the DiRAC directors as well, is going to be speaking on an exciting topic then. Mario, is there anything you want to add before we wrap up? All right. Thank you so much, everyone. Have a wonderful night and join us on Instagram Live.